Hello, we're going to look at the arc length and the angular speed as well as the linear speed. Okay, we'll start off with that. And this is still from your chapter 6. We're still on chapter 6. And so let's look at this. 6.1, so we're going back to 6.1 because there were some concepts that I wanted just to come back to afterwards. Okay, and so arc length and angular speed. So we want to determine or find out what they are. Okay, so let's look at the circle. Okay, and here we see theta. Okay, our angle theta. R is your radius, and S is your arc length. So note that, remember that the circumference of a circle is 2 pi r, okay, or pi d, because the diameter is equal to twice the radius, or the radius is half the diameter. So we know that all the way around, okay, the circumference is 2 pi r, okay? So we have to do all the way around, take in consideration the radius, okay, of the circle. All right, so now note that if I just have this piece right here, this portion of the circle, okay, theta will be theta out of 2 pi, okay? So that's the fraction of the circle. That's why it's written as, like, this is the sector, theta over 2 pi, all right? And so therefore, when we find the arc length, this right here, we find this arc length, we know that the arc length, okay, so we're dealing with this piece right here. So if we look at the whole part, the 2 pi r, and then just take a fraction, multiply that by the fraction of what we need, that's where the theta over 2 pi comes from. Okay, so the arc length is theta over 2 pi, which is this fraction, times 2 pi r. Okay, so I'm just taking a fraction of the circumference. All right, and so when we do that, we end up with theta times the radius. So that's how you get the formula for arc length is equal to theta times the radius. All right, so now that we looked at the arc length, let's look at the examples in your book. This is on page 473, number 57. It says, find the arc length of a circle with the given radius r and the central angle theta. Give the answer in the given unit of measure and round decimal to the nearest hundredths. So here we have the radius is 4 inches and theta is 1. So again, we use the formula for arc length. So we have S is equal to theta times R. Theta is 1 and the radius is 4, okay, or 4 inches. And so therefore we just get 4 inches. Okay, there you go. Now notice in 58 that we have the radius is 9 centimeters, but theta is in radian, okay? And so we still use the same thing, but to round it to the nearest hundredths, we have to convert the pi to numerical form, okay? So basically we still have S is equal to theta times R or R times theta, okay? You might see it in the book as R times theta, okay? It doesn't matter. All right, so we have what, pi over 2 times 9. And so that really gives us what, 4.5 pi, okay? And so what you do is use your calculator and find out what that gives you. So you have 4.5 times pi. And then you hit enter, okay? You would get 14.13716,694, and we want to round that to the nearest hundredths. So that means that you get 14.14 centimeters, okay? All right, and so there, that is dealing with the arc length. All right, so if we look at we're going to look at another one. We're going to look at 61. Okay, now 61 is different. Okay, 57 was different, 58 is different, and 61 is different. Okay, but they all work the same way. So what we're going to do, let me put it right here. 61. This time you're given that R is equal to 16.5 meters and theta is equal to 30 degrees. All right, so here, you remember how we were talking about the difference between degree and radian, okay? And how radian is used in the mathematical context and degree is not. So here we would have to convert your degree to radian form, okay? And so we already know how to do that, okay? So we have 30, and how do we do that? All right, so pi over 180, very good, okay? So you already know how to do that. So you get pi over 6. So 30 degrees is equivalent to pi over 6 radian. And so now that becomes just like 58. Okay, so again, we go through the same process. S is equal to theta times R. All right, so we got pi over 6, and then R is 16.5 meters. Okay, and so basically this is over 1. So again, when you multiply the top, multiply the bottom, and divide. So we can just multiply the top pi times 16.5 and just divide that by 6. All right, so we'll do 16.5 times pi. Okay, that's going to give you like 51.836278878, and divide that by 6 times 1 is 6. So divide that by 6, and you get to the nearest hundredths, 8.64. Okay, so you get 8.64. And that's meters. Okay, and so arc length is really dealing with the circumference. Okay, and so the units is just linear. Okay, so that's why we have meters. So that's how we have inches, and that's why we have centimeter. Okay, so that's dealing with the arc length. Okay, so now let's do another page, and we're going to go to the angular speed as well as the linear speed. Let me save this. All right, so we'll save that there. All right, and then we will create a new. All right, so let's look at the angular speed. Okay. And so the angular, when you think about angular speed, what comes to mind? Okay, an angle. All right, good. So this is mainly dealing with your angular displacement. Okay, so if we look at, think about a carousel, okay, like the hoppy horses on the Ferris wheel. All right, I mean on the merry-go-round. All right, so if we look at this, and let me draw, this is the center, and let's suppose we still have, there we go. Okay, and so we have that. All right, and so we're going to do, what I'm going to do here is, it's going to have 2. So I'm going to do, okay, that'll be the first level, and then we'll do this one as the second. And let's do, this is 1, and this is 2. And going this way. And that's the angle. All right, and so we'll put, this is V. And, you know, from here to here, that's that radius. And from this to that, that's that radius. Okay. But in angular, we're just dealing with the rotation here. Okay. So angular speed, we're actually dealing with the rotation. Okay. Of this angle. So we're dealing with the rotation. Okay. That's rotation. The rotation will be the same. See? From here to here. All right. So basically, so the angle of rotation would be the same for 1 and 2. Okay. So let's say for 1 and 2. We'll say this is horse 1, this is horse 2. So that angle of rotation will be the same. It's almost like you're on the track. You know how they have, it looks like, you know, they're doing, some are running longer, but the angle is the same. Okay. All right. So the angular speed, okay, or the angle of rotation will be the same for 1 and 2. All right. So to find the angular speed, so angular speed, okay, will be omega. It's represented by omega is equal to, and this is the theta. Okay, so that's the theta over time. So T is time. Okay. And so that's how you find the angular speed. All right, so if we look at all right, so we want to look at an example. And this is coming from, well, let's look at the linear speed because the problem that you have is that I'm going to give you is 81, and we have to find the angular and the linear speed. So let me talk about the linear speed first. All right, so do we have the angular displacement, angular speed, okay? We're related to a carousel or even the track, okay? All right, and so we have this runner and this runner, or horse, or whatever you want to call it. All right, they have the same angle of rotation. So I'm going this around, okay? But angular speed, okay, omega is theta, okay, that angle divided by time, okay? And so that would give you your speed. All right. All right, good. So that's angular speed. So ruminate on that. All right, so let's look at the linear speed. Okay, so this deals with distance. So when you think about linear, what do you think about? Okay, a straight line, right? Okay, so basically we have to incorporate, see, this is a line, straight line going this way, okay? We have to incorporate the distance here, okay? So from here to here, this radius here is less than this radius from here to 2. So the distance of different. All right. So 2 is further than 1. So basically the velocity v, okay, so linear speed v Okay, that's V. Okay, angular is omega. Looks like a W. It's omega. All right, V is equal to S over T. Okay, and so notice this is theta over T. Okay, and then the velocity right here is like dealing with this. Okay, over T. And so the angular is dealing with this rotation here, but the linear, okay, is dealing with the arc length. All right. And so we have basically S, which we know is theta times the radius, okay, over time, right? Now, looking at this, what do you know? What do you see in here? Well, look, that's right here. So we can replace the theta over time with omega. So basically, linear velocity incorporates the angular speed, okay, times the radius. And so this is your linear speed. So we need the angular speed in order to get the linear speed. Okay. All right, so we looked at these. So look at them carefully. Okay. So angular is dealing with the angular displacement. And if you notice that the angle of rotation for 1 and 2 are the same. Okay. But the angular speed would depend on the time. So omega is equal to theta over time. But the linear speed deals with the distance. Okay, so 2 is further away from 1. So that's the difference. That's the distance here. Okay, so linear speed is S over T. And S is your arc length, which is theta times R, and that's all over T. But theta over T is omega. So we got those two. So all right, so we have the formulas. All right, so we're going to do examples. Example from, I'm going to go back to another example that I omitted for the arc length. Okay, but we'll come back to it. All right, so we have number, let's do 81 on page 474. Number 81. Now it says that an industrial circular saw blade, okay, has a 10-inch radius and spins at 1,000 revolutions per minute. Okay, so we have, let's see, we have something like this. We'll put it like this. All right, pretend like that's a nice circle. All right, this blade. All right, so we got a circular saw blade, has a 10-inch radius. So 10-inch radius. So R is equal to 10. All right, and then it rotates or spins at 1,000 RP minute. Oh, and that's the other thing. Okay, and we'll talk about that. I didn't quite get into the units that is normally in. I didn't put that. All right, so we are given the radius, and it says rotates at this. Okay, so it rotates at 1,000 revolutions per minute, right? And so note that thing to note is that 1 revolution is equal to 2 pi radian. Okay. All right, so it says that find the angular speed of a tooth of the blade in radian per minute. So A, we have to find the angular speed. In radian per minute, okay? So radian per, let's say radian, oops, radian per minute. Radian per minute. Okay, so we know that angular speed is omega is equal to theta over time, right? Okay, and so we are given the we're actually given the angular speed at 1,000 revolution per minute. Okay, so because it rotates, it said it rotates, so that's at an angle. Okay, that's the rotation. All right, so we just need to convert 1,000. Uh-oh, run out of space. All right, so 1,000 revolutions per minute. So in other words, put it like it is, per minute. Okay, we need to convert that to radian per minute. Okay, this is revolution. All right, let me just stretch that over. Okay. All right, so that's revolution per minute. Okay, and so 1 revolution is equal to 2 pi radian. All right, so we got 1 revolution is equal to 2 pi radian. See how I did that? All right, and I did that so that the revolutions would cancel. So the revolutions cancel, okay, and that's going to leave us with radian per minute, and we need to be in radian per minute, okay. And so what we get here, we get 2,000 pi radian per minute, okay, and that's what the angular speed is. Angular speed is 2,000 pi radian per minute, okay. And so now I need to find the linear, okay. So B says the linear speed of the tooth, find the linear speed of the tooth in feet per second. So I need to do linear speed, and these end up in feet per second, okay. All right, so, okay, let's see, we need some space. Need some space. Okay, so I'm going to go up here. Let me go up here for space for B. All right, so remember that linear velocity is equal to the radius times omega, which is found the angular speed. So, and then the radius is 10, right? So we have 10 times 2,000 pi, okay, and then that's radian per minute, and we need to have it in feet per second. So we have to do a lot of conversion here. So here we need to end up in feet per second. Now, okay, so now we can convert put in the pi radian, okay, in there. But let's look at the minutes, okay? So minutes can be converted to seconds, right? And we have, oh, this is inches, 10 inches. 10 inches. We have to convert the inches to feet. So what's the relationship between inches and feet? So we know that 12 inches is equal to 1 foot, okay? We got that. And then we have, and for minute, we know that to seconds, we know that 1 minute is equal to 60 seconds. Okay, so notice how I put the minutes on top because this was at the bottom, and I put the inches at the bottom because this was at the top. I need them to cancel out. All right, so let's look and see what we have so far. All right, so we have, let's cancel. We can cancel out the inches. We can cancel out the minutes. And that leaves us with feet per second. All right, so let's do the multiplication at the top. So you have what? 10 times 2,000. Okay, and I'm leaving in that still pi, and we'll go ahead and put your multiply that by pi because we have to, yeah, round the answer to the nearest hundreds. Okay. All right, so we have times pi. Okay. And so we'll have, that's too light. All right, 62831. Okay. And then that's 0.85307. So I'm not rounding to the very end. And then that's going to be divided by, and that's what's on top, feet. And that's over, then we got to multiply 12 times 60. 720. All right, so now let's do the 62831.85307 divided by 720 to see what we get. All right, and so we get, you should get 87.27 feet per second. Okay, so notice here we went ahead, and radian just goes away. Okay, it's really not, you don't have to put that there. So we have convert the pi to 3.14 or just pi. Okay, 22/7. So you have the whole thing. So you have to do 10 times 2,000 times pi, and then at the bottom do 12 times 60, divide that to get your final answer. So we've incorporated the angular speed, okay, as well as the linear speed. But the thing is, you have to know, okay, what are we given? Okay, we were given the radius and we were given the angular speed. However, they wanted the angular speed in a different unit and radians per minute. So we converted that to radians per minute. But you have to know when you're dealing with revolution, one revolution around is 2 pi radian. Okay. All right. One revolution, one rotation around. Okay, that's 2 pi radian. So good. So that was number 81. Okay, on your page. All right. So look at those for your homework. I've already sent that out by email. Okay. All right. So if you have any questions, let me know, and I'll be happy to help.